Good day, everyone, and once again we're back together. All right, we're looking at that 2023 November exam. All right, so if you haven't subscribed, please just make sure you're part of the family. All right, so let's start with the multiple choice question, and I hope for those of you who've just recently written this exam that you will actually find these answers quite interesting and that you did the right thing, of course. All right, let's get right into it. So the first question, they say to us, we've got a constant net force which is applied to a block. Which one of the following statements is correct? Now, please note, the moment we talk about a constant net force, remember Newton's second law, that a net force will always, result in an acceleration, right? So we know that if we've got a constant net force, then we will have a constant acceleration. We don't need to dream up anything else. The answer there should be B. Right, and then they say a crate of mass M is stationary on a plane that is inclined at an angle theta, which is with the horizontal rather. They say which one of the following statements regarding the magnitude of the frictional force acting on the crate is correct. Now, if we were to go and, just draw a free body diagram for this guy, right, you note that, of course, if we were to let it go, it should slide down, ideally, but it doesn't. They said it's stationary, so we know it means that friction would be opposing the motion going down, right? So that's static friction, actually, and not kinetic, okay? And in this case, we know that the parallel component of gravity would actually pull it down, right? So as a result, we know that, those two would be opposing each other. So they say the magnitude of the frictional force acting on the crate rather, is, all right, so they say equal to the component of the weight of the crate, which is parallel to the plane. Absolutely correct. So our answer there should be A. Okay, right, let's go on to the next one. They say a ball is projected vertically upwards from the top from the top edge rather of a building. They say points P, Q, R, and S represent different positions during the motion of the ball as shown in the diagram below. They say ignore the effects of air friction, right? They say between the 2 points, between which 2 points will the ball undergo the greatest change in kinetic energy? All right, now remember that kinetic energy is not a function of the direction of the ball, right? Now, if you think of it, suppose we, for argument's sake, we say the ball started with an initial velocity of 5 meters per second there, right? Of course, it would come back to the same point with a velocity of 5 meters, or rather with the speed of 5 meters per second, right? If we chose up as positive, this would be negative, right? And suppose, let's say, it gets to the ground at 20 meters per second, right? Now, if you were to take the kinetic energy here for 20 meters per second, minus the kinetic energy there for 5 meters per second, that you get an answer. However, that answer would not be greater than if we took 20 minus that point where it is at 0 meters per second, right? So the greatest change in kinetic energy should actually be between the points Q and S. And that answer is in D. Okay. Right, I hope that makes sense, guys. All right, so they say to us a ball is dropped from a height h and strikes the floor with momentum p, right? Now, how would height be related to, momentum? So if you think about momentum, we know that momentum is mass times velocity. However, we can relate velocity to the height, isn't it? If you think of equations of motion. So they say to us it's dropped, suggesting that our initial velocity is 0, right? So we want to find out what would the final velocity be when it actually lands on the ground. Okay, so we can use equations of motion and say, look, we know Vf squared right? So if we use the formula Vf squared is Vi squared plus 2 times g delta x, but we know our delta x is height there. We know initial velocity is 0, right? That's 2g multiplied by the height. So meaning if we wanted to find the velocity, it would be the square root of 2 times gh, right? So that's our first velocity, right? So which means this velocity here would be square root 2 gh. Okay, so that's how we'd get the first momentum. So they say which one of the following represents the momentum of the ball when it strikes the floor after being dropped from height half h. So we will do the exact same thing. However, we're looking for the other velocity. Let's call it v2, right? So for v2, the second velocity when we drop it at a different height, it would actually be the same formula. The only difference is that now instead of h, we've got a half of h, right? And if you look at that, what are we going to have? So that's 2 multiplied by 1 over 2, that gives us 1. So we've got the square root of gh, right? Now I want you to note, ladies and gents, so meaning if I'm looking for this new momentum now, let's call it momentum 2, it would be mass multiplied by v2, right? So that's mass times, in this case, the square root of gh, whereas in the initial one we had square root 2 gh. So which means momentum 2 is actually square root 2 less than the first one. Okay, so P2 would actually be, if you look at this, it would be P divided by square root 2. Because if you think about what P was, P is M times square root 2 times square root of gh, right? And if we divide that by root 2, that cancels with that, and we're left with m times square root of gh. So it means it's P1 divided by square root of 2. So in this case, that would be, the answer is B. So these are the kind of questions that do require a little bit of working out. If you remember my advice, I said some multiple choice do require quite a bit of working out, right? Okay, let's go on to the next one. They say a box moves on a horizontal surface, right? They say the diagram below shows all the forces acting on the box, right? They say which one of the following combinations of forces do work on the box. Now there'll be only two forces that do work on the box. That would be Q and S, because remember the normal force, which is P and R, in this case the box does not move vertically, right? So there's no work done there. So it would definitely be Q and S. Okay, right, so let's our answer there should be B. Okay, I hope that makes sense. Right, moving right along, they say a train moving at a constant velocity towards a stationary listener, right? So remember, first of all, it is towards, right? They say this train emits sound waves at constant frequency, right? They say which one of the statements about the sound waves observed by the listener is correct. Okay, so we need to remember the train is moving towards, so definitely the frequency of the observed frequency rather should be higher than the one that is emitted. Okay, so the observed frequency is higher than the emitted frequency, definitely. Okay, right, I don't need to discuss that further. Our answer is A there. Right, now they say to us, refer to the diagram that is below. Q and R are small spheres suspended by light insulated strings. They say when a negative charged rod is brought close to Q, where Q is repelled, okay, sphere Q rather is repelled, right? So what does that mean? Remember that like charges repel each other, so that does tell us that Q should be negative, right? Okay, so and what about R? They say when the negatively charged rod is brought close to sphere R, sphere R is attracted, so that does tell us that R must be positive, right? So they say which one of the combinations below can be possible for the nature of the spheres of on spheres, rather the nature of the charges rather on spheres Q and R. Okay, we did say Q would be negative and R positive, right? So do we have such a combination here? We've got negative, okay, we've got positive and neutral, okay, and okay, right, so we do not have negative and positive, right? But it is possible that, you know, for instance, for us rather to have negative and neutral, right? So it's possible that if we look at sphere R, that would definitely be neutral, because in that case what would happen is that the positive charges would definitely be attracted towards sphere, the negatively charged rod. Okay, so we can have D as an option there. All right. Okay, so as we move right along, now they say 4 voltmeters V1, V2, V3 and V4 are connected in a circuit as shown in the diagram below, right? So they say to us which voltmeter will have the same reading as voltmeter V1 when the switch is open. Now remember, when the switch is open, it means that there's no current that's moving in the external circuit, right? So now I want you to note what happens is that V1 will actually be the reading of the EMF, right? Because in a sense, it is the reading across, the terminals of the battery, right? So the only other one that would be equal to the EMF would be V3, because if you look at V3, the one leg of it is kind of connected to the other side. Now remember, the resistor does not become a resistor unless there's current, so it just becomes another conductor, and the other leg of that voltmeter is actually connected to the other side of V1, so it is V3 only. Okay, and then right, let's go to the next question. They say to us a split ring commutator. Now remember, once we've got a split ring commutator, right, we know that we're dealing with direct current, isn't it? Okay, so they say to us which one of the combinations below is correct for the magnitude and direction of the induced current in the external circuit. Right, so the magnitude of the induced current, definitely it would change, right? Because remember, in this case, what you'd have for DC is actually something like this, right? So it would constantly be changing. However, when it comes to the direction of the current, it should be the same. The direction should always be in the same direction, hence direct current, right? So we know that the magnitude of the induced current changes whilst the direction is constant. Okay, so our correct answer there should be C. And finally, they say to us, a light of a suitable frequency is shone on the metal surface, right? On the surface of a metal, and electrons are ejected from the metal. Right, they say which one of the following is equal to the ratio of the work function to the threshold frequency. Now remember guys, when it comes to the work function, we know that the work function is HF0, where this is the threshold frequency. So if we're taking a ratio, it means we're dividing them by each other, right? So dividing this by the threshold frequency, right? Of course, what we do on the left, we do on the right. So what happens? It means this guy here would actually cancel. So the ratio of the work function to the threshold frequency is actually Planck's constant. Okay, so in that case, our answer is definitely A. All right, and that is how the cookie crumbles when it comes to the multiple choice section. I hope that made sense, ladies and gents. All right, let's move on to the next question. Moving on to question 2. All right, let's have a look at it. They say we've got 2 blocks of mass. So we've got block A of mass 4 kg and B, and which has a mass of 9 kilograms that are connected by light inextensible string. The blocks are held at rest on a plane which is inclined at an angle of 35 degrees. A constant force F acting parallel to the plane is applied to block B, as shown in the diagram. The blocks now accelerate up at 2 meters per second squared. All right. So they say state Newton's second law of motion in words. All right. I think you guys should be able to do this by now. Right. If a resultant force acts on a body, the body will accelerate in the direction of the resultant force. And that acceleration is directly proportional to the resultant force and inversely proportional to the mass of the object. Otherwise, you can use the other definition that says resultant force acting on an object is equal to the rate of change of momentum on a body. All right, now let's quickly have a look at what we are being asked there. They say the kinetic frictional force acting on block A and B are 5.88 and 13.23 respectively, right? So they want us to draw a labeled free body diagram showing all forces acting on block A. Right, now looking at block A, okay, I'm going to, so looking at block A, what would be the forces acting there? Now it would be the force that's exerted by the string, or you can say the tension on the string. Okay, we also have frictional force. We know that this is going to be opposing the motion, so that would be frictional force. Okay, we've got the normal force, and by the way, please remember that the number of forces is actually indicated by the number of marks as well, right? Normal force as well as, okay, in fact, let me do this, as well as gravitational force. Now, please remember that gravitational force acts vertically downwards, right? Or we can say this is the weight on the object, right? So these are the forces that are acting. Of course, nothing wrong if you decided to put in the components of the force, right, of the weight rather, which is the perpendicular and the parallel component of the weight. Okay, right, so let's go on to the next question. Okay, let me just take this up a little bit. Okay, so that we're not really too far off. Okay, so they say calculate the magnitude of the tension in the string. Right, now what we want to do, ladies and gents, is let's start with block A because we've got most of the information that we need, right? So instead, what I'm going to do is let me, for the free body diagram, so I know I would have the tension on the string, I'd have the friction. Okay, let's say that's TS, right? That's friction, that's kinetic friction, so I'm going to call it FK. And now, instead of drawing the weight, let me rather put in the components. Firstly, it would be the parallel component of the weight. Okay, so that would be weight parallel, and the perpendicular component of the weight, let's call it weight perpendicular, or you can call it FG perpendicular, right? And the normal force. Now remember, we know that this body is actually accelerating upwards, right? So what we need to do is focus on the forces that are parallel to the incline, right? Because that is where the acceleration is occurring. So we are going to simply say, right, so F net is equal to MA. We're going to take the direction of motion as our positive, so we're going to take direction upwards as our positive direction, right? So that's going to be the tension on the string minus the frictional force on B minus the weight parallel for B, and this is equal to MA. We're given friction. They said friction is 13, or for block A rather, this is going to be, friction is 5.88, right? So this would be 5.88 newtons minus. Now remember, when we want the parallel component, we always say this is equal to M times G, the sine of the angle of elevation, right? So it's going to be the mass, which is 4, times 9.8, the sine of 35. And this is equal to, again, this is 4 times. And our acceleration, they did say to us that it's accelerating at 2 meters per second squared. So that would be 4 times 2. Okay, so that can give us the acceleration. All right, so let's try and get that. So we know that we'll have 4 times 2. Okay, plus 4 times 9.8 sine 35 plus, this is 5.88. Right, and I get a value. Am I correct there? Oh yeah, that's because I said that's minus instead of plus. Okay, so let's delete that. Let's put a plus. Okay, I'm not sure what did I do there. Okay, let's start this afresh. So this is going to be 5.88 plus 4 times 9.8, the sine of 35, plus 4 times 2. All right, there we go. Got 36.36 newtons, and that is our tension, right? Having used body A. All right, so in this case, let's go to the next one. They want us to calculate the force F. Now remember, force F is related to, or rather is directly connected to the 9 kilogram body, which is block B. Okay, so I'm gonna draw the free body diagram for block B, and what it looks like is we've got the force applied, which is F. Again, we've got friction. Okay, and we've got the weight parallel. All right, and we also have, right, I'll just try and draw a big dot there so that I can fit in all my forces. We also have the tension, right? So there it is there. Of course, the usual suspects, normal force, as well as the perpendicular component of gravity. Right, so in this case, because I'm looking for force F, again, we know that this is going to be F net equal to MA, but remember this time I've got force F, which is going up, minus friction for B, minus the tension, minus the weight parallel for B, and this is MB times A. Right, so that's force minus, they gave us, this is 13.26 if I remember, 23, the friction, minus the tension, right, we found this guy to be 36.36, minus weight parallel, that's going to be 9 mass times 9.8, the sine of 35 degrees, and this would be equal to 9 times 2. And that's how we're going to get that force F there. Okay, let's try and do our gymnastics there. 9 times 2. Okay, plus, you see there I'm typing minus again. 9 times 2 plus, and 9 multiplied by 9.8, the sine of 35. Please make sure that your calculator is in degrees, right? Okay, plus 36.36. Now remember, everything changes, becomes positive when it goes to the other side, and plus 13.23, right? Okay, and please, you can verify this for me. I get a force of 118.18 newtons. Okay, right, so that is the answer that I get in terms of the force F that is acting on block B. Right, let's go on to the next question. They say to us, the angle that the plane makes with the horizontal is now decreased. Now remember, once we decrease the angle, ladies and gents, it will affect the normal force, right? Now, I'm going to show you just now. They say, how will this change the kinetic frictional force acting on block A? Choose increase, decrease, or remain the same. Right, so that will increase the, the amount of friction that the body experiences. Okay, so 2.4.1, once we decrease the angle, we will increase the amount of friction. So that would be increased there. All right, and why would it increase is the question, right? So they want us to explain the answer to 2.4.1. Right, so in this case, an increase in, okay, let me just do this. Right, so when you look at the normal force, right, an increase in the angle, okay, I just made a mistake there. An increase in the angle would actually decrease the normal force, right? And if the normal force increases, we know that friction is coefficient multiplied by the normal force. So that means that normal force is directly proportional to frictional force. A decrease in the normal force will, an increase in the normal force rather, will increase the frictional force. Okay, I'll say this again, right? A decrease in the angle, right, will increase the normal force of the body, right, and or that is experienced by the body, and as a result, friction is directly proportional to the normal force. So an increase in the normal force should increase the amount of friction. Okay, right, and that is how the cookie crumbles, as we're going to go to question 3 next. Moving on to question 3, let's go. So they say to us we've got a ball of mass 0.5 kilograms, which is thrown vertically upwards from the top edge of a building, which is 15.3 meters high. The ball reaches a maximum height of 5.89 above the top of the building. The ball strikes the ground and bounces vertically upwards, reaching a maximum height at ball P, as shown in the diagram below. Right, so they want us to ignore the effects of air friction. Of course, that does tell us that we are dealing with vertical projectile motion. Right, they say define the term free fall. Right, so remember that when we talk about free fall, this is the motion of any object under the influence of gravitational force only. Okay, right, so the next question, they say using only equations of motion, calculate the speed of the ball, the speed at which the ball was projected upwards. All right, now several things that we know, ladies and gents. So I am going to kind of label this, right? So if we label this right from the beginning here, let me use a different color. Okay, so if we label it right from the beginning here, okay, let's call this A, let's call that B, okay, let's call that C when it returns to the same point, and let's call that D, right? When it leaves the ground, let's call that point E. Right, so what actually do we have, right? We wanted to find out with which speed was it projected. If we take information from A to B, we know what happens at B. The velocity becomes 0, which is maximum height. Okay, we know acceleration, and we know the height in this case was 5.89, isn't it? So I'm going to take information there, all right, from A to B, and say, well, we want to know initial velocity. Our final velocity is 0. Acceleration. Now, I'm going to take up as positive if you don't mind, right? So which means I'm going to have negative gravitational acceleration, because remember, it always moves vertically downwards. Our time is unknown, but we know that we projected the ball 5.89 meters above where it was projected from. So that's 5.89. It will be positive because it was actually upwards, right? So we're looking for initial velocity, but we don't have time. So which equation of motion would that be, right? That's Vf squared Vi squared plus 2 times a delta x. Of course, our delta x in this case is delta y. Okay, so we said that's 0. We're looking for this guy. That's negative 9.8. And that's 5.89. All right, if we take this to the other side, that's 2 times 9.8. So that's 2 times 9.8 times 5.89. Okay, and we know this is going to be Vi squared is equal to that. Now, if we take it to the other side, we have this as positive 115.444, which is equal to Vi squared. And of course, we're going to take the square root on both sides. And remember, when we take the square root, that becomes plus or minus, but we need to choose which one we go with, right? So we're going to say, okay, so we're going to take, there we go. So our initial velocity is 10.74. So we're going to take the positive square root, and the reason for that is that it was actually projected upwards, right? Meters per second upwards. All right, so there we go. However, they said the speed, so there was really no need for me to mention direction. Okay, right, and then the next question, they say after the collision with the ground, the ball leaves the ground with a speed of 11.92. right? They want us to calculate the amount of kinetic energy lost by the ball during the collision with the ground. Now, what we're going to have to do is we're going to have to find out what the velocity is when it reached the ground, right? So meaning in this case we want the velocity at d, right? And then so that we can now compare the two kinetic energies between d and e. And remember, we are given the the velocity when it left, which is at e, which is 11.92. Right, so let's do this. Let's find out from a till d, right, what was the final velocity. And nothing wrong if you decide to take the from b till d. In fact, let's do that. Let's take b to d, right? So that would be 3.3. Okay, so from b to d, remember at b it was at maximum height, so our initial velocity would be 0. Okay, our final velocity is what we're looking for. That's minus 9.8. The time is still unknown, but we know what height it was at. Now, from b to d, you'll see that it's this 5.89 plus the 15.3, right? So let's add that up. So that's 5.89 plus the 15.3. You get 21.19. And there's nothing wrong. You could have used A to D. You would have used the displacement of 15.3 in that case. Right. So there's our displacement, and remember it's displaced downwards, so that's going to be negative 21.19. Remember we said up is positive, right? So again, the very same formula, because we're looking for final velocity this time. We don't have time. That's vi squared plus 2 times g delta y. Okay, our initial velocity is 0. That's 2 times 9.8, negative 9.8, and that's negative 21.19. Sorry about that. That's negative 21.19. Okay, and we're going to take the square root again, so I might as well just do that. Okay, so that's going to be 2 times 9.8 times 21.19. Okay, and we get a final velocity of, now remember ladies and gents, I said when you take the square root you get plus or minus, right? So this would be minus 20.38. Okay, right. So why is it negative? Because it was heading downwards, so our final velocity there is negative because it was going down. Right, now they wanted the change in kinetic energy, right? That was the question, the amount of kinetic energy lost. So I am going to say, right, let's find out the change in kinetic energy. So I'm going to say this is kinetic energy final, meaning this is after the collision, okay, when it left the ground, minus kinetic energy initial. This is before it touched the ground, right? So that's going to be half m, right? That's Vf squared minus Vi squared. So you should be very careful here. The mass of the ball, 0.5. All right, so our final kinetic energy, now remember this is when it left the ground, right? So if you look at final and initial as, this would be before, so this would be our Vi, and afterwards this is after the, when it bounces off the ground, right? So our final kinetic energy was that 11.92 rather. Okay, that's squared minus the negative 20.38, and there's really no issue if you took it as positive in this case. We're just looking at the speed, right? So in this case, we're going to say, right, this is 0.5 times 0.5, okay, and this is multiplied by 11.92 squared minus 20.38 squared. Okay, right, and what do we get there? Right, the change in kinetic energy is actually negative 68.31 joules. So that's the amount of kinetic energy that was lost. Okay, and that negative isn't telling us about direction, but merely telling us about the fact that we lost that kinetic energy in the ball, right? Okay, so that is it. So the next portion, they say to us, the velocity time graph for the motion of the ball from the instant it is projected upwards from the top edge of the building until the time it reaches point P is shown below, right? Now they say to us, write down the numerical values indicated by each of the following. So in K, right, so I want you to note, first of all, let me start with L, right? So this would be the initial velocity of the ball. What was that initial velocity? We found it to be 10.74, right? So this value here would be 10.74. Okay, so let's just write it like that. Okay, and then we've got K. So K, remember, it went to maximum height, reached the ground. This is the velocity with which it reached the ground. So K would be the velocity with which it leaves the ground. So K rather, would be the 11.92 that was given to us. Okay, and we're given there T2 minus T1. All right, so the difference in time there, were we given anything related to time? Okay, right, okay, well, now I want you to please note, ladies and gents, when it comes to that time there, there was really nothing given in terms of time, and I'm not sure why they gave this 1 mark. All right, however, we know in this case that this is the time from when it left the ground. Were we given anything in terms of time? Okay, the speed. Oh no, actually I skipped a question. All right, so that's why I actually skipped a question. So 3.3.2, they said to us, calculate the time taken for the ball to reach point P after leaving the ground. So yeah, that's why. So to answer that question, what I'm going to do, all right, sorry about that. Okay, let me answer it over here. So the time that it takes to actually reach the ground, after leaving the ground, right? So remember the initial velocity in that case, this is now according to our sketch, this is from E to P, right? So from E to P, our initial velocity would be 11.92. Okay, our final velocity would be 0. Remember, it reaches maximum height. That's minus 9.8. That's gravitational acceleration, and we're looking for time, right? So we're going to use the simplest equation of them all. Vf is equal to Vi plus G delta T. Apologies for that mess there, right? So final velocity we said that's 0. Initial is 11.92 plus, in this case we've got at negative 9.8 delta t, and if we take everything to the other side, minus 11.92 minus 9.8 delta t, and we're going to divide both sides by negative 9.8, and we've got 11.92 divided by 9.8, and that gives us a time of 1.22 seconds, right? If we're rounding it off. So that tells us that T2 minus T1 should actually be exactly that time, which is 1.22 seconds, right? All right, so there we go. We've got LK as well as T2 minus T1. All right, ladies and gents, that is how the cookie crumbles for this question. I hope that you understood that. We'll continue again with question 4. Right, looking into question 4, let's get going. Right, so they say to us we've got a wooden trolley of mass 2.7 kilograms that moves to the left with a constant velocity of 3 meters per second. They say a bullet of mass 0.03 kilograms is fired horizontally from the left towards the trolley. Okay, so they say the bullet strikes the trolley and comes to rest inside the trolley in 0.02 seconds. The average net force exerted by the trolley on the bullet during this time is 591 newtons, and they say the bullet trolley combination now moves to the right according to diagram 2. All right, now they say ignore all frictional and rotational effects. Well, I had a couple of issues with this question, but we'll address those issues a little bit later. All right, so they first say to us, write down the magnitude and direction of the average net force that the bullet exerts on the trolley. Now, obviously, we know according to Newton's third law, right, that if body A exerts a force on body B, then body B will exert an equal but opposite force on body A. So, if the trolley exerts a force of 591 on the bullet, right, then obviously it means that the bullet will exert an equal but opposite force on the trolley, right? So we know that the force that the trolley exerts on the, or rather that the bullet exerts on the trolley, so the magnitude of that force will be 591, right? So that will be 591 newtons, but of course it will be to the right. Okay, right, so there we go. Now 4.2, that's where really I had some issues, but nonetheless, as I said, we'll discuss it. They say calculate the magnitude of the velocity with which the bullet strikes the trolley. Right, now if you think about it, what happened to the bullet? Right, so here's the trolley, here's the bullet. Okay, so just before the trolley entered, or rather the bullet entered into the trolley, right, it had a velocity. Okay, let's call that velocity v initial. But then it went into the trolley and it stops at some point inside the trolley. Okay, I'm really trying to draw a system that you guys can really thoroughly understand. Okay, so there's the part of the bullet, and it stops at some point inside the trolley, right? So now I know that the velocity of the bullet will be 0. It stops, right? Now the issue that I had with this question is that when you look at it, you have to kind of ignore the fact that as the bullet entered into the trolley, it started changing, the velocity of the trolley automatically, and just focus on the bullet on its own as though it was just, just moving on its own in a sense, right? But the reality is that, obviously as the bullet starts entering, it changes the velocity of the trolley. Even if it's going to be embedded, there's going to be a velocity change within the entire system. But to whoever was, developed this question, I think really there's some thoughts that needed to be made here, right? But nonetheless, let's answer it in relation to what was expected of us, right? So they say to us, we've got, all right, so we wanted to find out what the velocity of the trolley is, right? So remember the impulse momentum equation. So F net delta P, delta T rather, is equal to the change in momentum. So we know that net force was 591. It took 0.02 seconds to actually stop within the trolley, and the mass of the bullet is 0.03, right? So we know the final velocity. So remember, this is going to be final velocity minus initial velocity. So the final velocity of the bullet was 0. The initial velocity is really what we're looking for, right? So what we're going to do is divide by 0.03 on either side, so that cancels with that, and we find the initial velocity of the bullet. Okay, let's do that quickly. Okay, so we're going to have 591 times 0.02 divide by 0.03. Okay, so we get 394. So on the other side, we get 394 meters per second. So the velocity will be a negative 394. And in fact, if we were going to consider the direction to the right, let's say as positive, okay, please keep in mind that the bullet exerted a positive force on the trolley, but the force that the bullet experiences would be negative because it's the trolley that's exerting a force on it. Okay, but nonetheless, we're looking for the magnitude of the velocity, so don't worry too much about it. Even if you got this positive or negative, what we care about is the magnitude. So, which means the velocity of the bullet before collision was 394. Look, you've heard me, register my misgivings about this question, but nonetheless, it is what it is. Okay, right. They say state the principle of conservation of linear momentum in words. Right. So please keep in mind in this case that in an isolated system, the total linear momentum is conserved. Right. So they say to us, calculate the magnitude of the velocity of the bullet trolley combination after collision. Right, so remember what happened. We had the bullet, right? So there's our bullet there. There was our trolley, right? Our trolley, they said, was moving at a velocity of 3 meters per second, right? So at 3 meters per second there, but after collision, we know both of them are now moving together as a unit, right? So there they are. The trolley and the bullet are now moving together. So we're going to take sum of momentum initial equals to the sum of their momenta final, right? So this is the momentum of the bullet, velocity of the bullet, initial mass of the bullet, velocity of the bullet, plus the mass of the trolley, velocity of the trolley initial, and afterwards both of them moved as one unit. So I'm going to add the masses and have a common velocity. Right, so we're going to have 0.03 times. Now we remember we need to take a positive direction. So I'm going to take the direction of the bullet, okay, as positive. So that's going to be positive 394, the one that we got there, plus Now remember, the mass of the trolley was 2.7, right? So that's 2.7. But the trolley was moving at a velocity of 3 meters per second, but in the opposite direction to the bullet. So this will be -3. And afterwards, right, the two join together. So that would be 0.03. Okay. And we want the final velocity. Right. So in this case, ladies and gents, what we need to just keep in mind, right, they did show us the direction. So remember that at the end of the day, that velocity will be a velocity that applies both to the bullet and the and the trolley together. Right, so let's calculate there. So we've got 0.03 multiplied by 394, okay, plus 2.7, that's multiplied by -3, right? So in this case, what do we get? Okay, we get 3.72, but now I'm going to divide both sides by the sum of these. So this would be, if I add 2.7 plus 0.03, this would give us 2.73, right? So I'm going to take my answer and divide it by 2.73, and I get a velocity. Okay, so divide both sides by 2.73, and the velocity after collision is 1.36 meters per second. Okay, right, and then of course this is to the right, or you can say to the east, depending on what you chose as your frame of reference. Okay, right, ladies and gents, that is how I would have answered that question, right? As I said to the examiners, I'm hoping that, our way of asking questions would really consider, some of the, practical issues that happen in physics. Of course, we cannot, cover all of them, right? But we need to somewhat make everything as practical as possible. All right, that's how the cookie crumbles on this question, right? So let's move on to the next one. Actually, this was 4.4. I'm not sure why I said 3.4. Right, so that's 4.3 and 4.4. Let's go to the next one. Right, let's jump into question 5. So they say to us, we've got learners that conduct an experiment to determine how the initial kinetic energy given to a trolley affects the distance the trolley moves on a rough horizontal surface. So that's very important. Okay, so rough horizontal surface means there's friction. So a learner pushes a trolley of unknown mass until it reaches point A with kinetic energy EKA. The horizontal distance traveled by the trolley before it comes to rest. Now that's important. So that means that at some point the trolley will have a velocity of 0, right? Is then measured. See the diagram below. Right, so they say the experiment is repeated with a trolley moving on the same rough horizontal surface with different initial kinetic energies of point A, at point A. Right, and the results are shown in the diagram below. Now note in this case, what are they doing? They keep pushing this trolley with different amount of force, giving it a different kinetic energy, right? And they are measuring the distance that the trolley will actually travel, right? So now they say ignore the rotational effects of the wheels of the trolley. Right, draw a labeled free body diagram showing all forces acting on the trolley during its motion after passing point A. Now remember, so we are not going to have an initial velocity after point A. Why? because we gave it an initial velocity and we let it go, right? So what actually causes it to stop would be the frictional force. So this would be the frictional force. Okay, and that would be, oops, let's try and draw that a bit nicer. Okay, so that's going to give us, this is going to be the gravitational force, or you can say this is the weight, as well as the normal force. Okay, so those are the three forces that are acting on the trolley. And please remember, guys, once you draw any additional force that is not part of the forces that are acting on that diagram, you lose marks, right? They apply, the markers will apply negative marking, right? Okay, so name the independent variable in this experiment. Well, what's the independent variable? What do we keep changing? It's the initial kinetic energy, right? So that would be the initial kinetic energy. All right. The next one, they say state the work energy theorem in words, right? So we remember that the net work done on an object is equal to the change in kinetic energy, right? Or you can say the work done by the net force on an object is equal to the change in kinetic energy. Right, now the next question, they say to us, calculate the mass of the trolley if the coefficient of friction between the wheels of the trolley and the rough horizontal surface is 0.18, right? So what we can do, ladies and gents, is that we can really say we know the net work done will equal to the change in kinetic energy. Now, what is our kinetic energy final? That would be 0 because the trolley stops, right? So EK final minus EK initial, right? So the initial kinetic energy will just have to take one of the scenarios here, right? And it doesn't really matter which one you decide to pick, right? Well, I'm just going to pick this one here. I know when I gave it an initial kinetic energy of 12, the distance that it will move is 3 meters, right? So I'm going to use that and say, right, so that's going to be my initial kinetic energy. So that would be 0 minus, that initial kinetic energy was 12, right? And then, now let's talk about the net force. What would be our net work done in this case? Remember, this object is moving horizontally, right? So, which forces are acting horizontally? That would be the frictional force. So that means that this is going to be friction multiplied by delta x, the cos of angle theta. Now remember, when we talk about the angle, we're talking about the angle between direction of motion and the force in question, in this case being the frictional force, right? So this means that our frictional force, and by the way, we didn't know what the value of the friction is, but you remember that friction is equal to coefficient multiplied by the normal force. And we know that the normal force in this case would most certainly be equal to the weight, right? So we know our coefficient is 0.18. That's multiplied by, now the normal force would be equal to the weight. The mass is what we're looking for, right? And we know gravitational acceleration is 9.8. So this would be 9.8 multiplied by, okay, so let me write this nicely. So this would be 0.18 into 9.8 multiplied by the mass. Okay, so let's find that out. So that's 0.18 times 9.8, and we get 1.7 1.64 m, right? So now let's use that frictional force there. So that would be 1.764 m multiplied by, now remember when we use that initial kinetic energy, we said the distance was 3, right? And multiplied by the cos of the angle between the direction of motion and the frictional force, that will be 180. Okay, right, so let's try and do that. So we've got minus 12 here, 1.76 times 3 times cos of 180. Okay, so times 3, cos of 180 is -1. So that gives me 5.292, right? So that will be -5.292 m, and we can divide both sides by -5.292. That's -5.292. And so what we get for our value of m, okay, that would be 12 divided by 5.292, and we get a value of 2.27 kilograms. Okay, and that will be our mass. That would be the mass of the trolley, and essentially that is how the cookie crumbles. All right, this was pretty straightforward. Okay, not really much to do there. Okay, I hope that you guys understood it as we move on to the next question. Right, so we begin with question 6. All right, so they give us then an ambulance that is moving away. Right, so we need to note that down. So that is moving away. So that means, all right, let's talk about that later. From a stationary listener with a constant velocity of 25 meters per second, the siren of the ambulance emits sound waves at a frequency of 550 hertz. The listener detects the frequency of these sound waves to be 512. So definitely you can see that the frequency, the detected frequency, is less than the emitted frequency, right? So the first question they say to us, state the Doppler effect in words, right? So we know that it is the change in frequency of the wave in relation to an observer who's moving relative to the source of that wave, or you can actually say it is the apparent change in the frequency of the observer relative to the velocity of the source, right? You can actually put it in any of those two ways. Right, so let's go to now the question 6.1.2, which has to do with the calculation. They say use the information to calculate the speed of sound in air. Now remember, in this case what we use is the Doppler effect equation, V plus minus VL over V plus minus Vs times Fs, right? Now what we do know in this case, all right, I'm going to take this down a little bit. Right, so we know the frequency of the listener was given to us as 512. I'm going to substitute that, 0.64, right? Now V would be the speed of sound, isn't it? So that is going to be V. Right, now the velocity of the listener, remember they said to us that's a stationary listener. So we know that VL is 0, right? And now we've got V. Now remember, we need the the left hand side to be less. So this fraction has to be a proper fraction so that we know we end up with a lesser fraction. So this would be V plus. Now the velocity of the source was 25. So that's 25 there, multiplied by, in this case, the frequency of the source, which was 550. And all we need to do, ladies and gents, is just to play around with some mathematical gymnastics. How you decide to do that, really up to you, right? Okay, so let's try and make it as simple as possible. Okay, right, so I've got, this is over 1, So I'm going to multiply numerator to numerator, so that's 550 over V plus 25, which is 512.64 over 1. So we can cross multiply there. So that's going to be 512.64 into V plus 25, which is equal to 550. Right, so I just left out the V there. Sorry about that. So this is 550V. Okay, so this is 550V as well. Okay, so we can multiply into the 2, and we've got 512.64V plus, what is 512.64 times 25? That gives us 12,816, which is equal to 550V. Right, I'm going to just multiply, or rather take this to the other side. Okay, so I've got 512V minus 550V. Okay, 12.64 minus 550. That gives us negative 37.36V. This is equal to, when we take the number to the other side, it becomes negative, so that's negative 12,816, and so we're going to divide by negative 37.36 and another negative 37.36. Okay, sorry about that. And so that's 12,816, and we're dividing it by 37.36, and I get a number 343.04. So V would be 343.04 meters per second. All right, so that is the speed of sound, right, in air. All right, let's look at the next question. So they say to us, if the ambulance moves away from the stationary listener with a constant velocity which is greater than 25 meters per second, how will each of the following change, right? So first they say choose increase, decrease, or remain the same. The speed of sound in air, that definitely remains the same, right? That does not change. Okay. The frequency of sound waves emitted by the siren definitely remains the same, right? So that's the sound of the source, so that would remain the same. The frequency of the sound waves detected by the listener. Now remember, if we're to increase that speed, that means that the detected sound waves would actually be even less. Okay, so you can imagine it. If you go to this formula, it means that the denominator becomes increases. Okay, so that means that your fraction gets smaller, and as a result, the detected frequency becomes smaller. So it would definitely decrease. Okay. Right, so that is how the cookie crumbles there. And then they say the spectrum of a distant star when viewed from the Earth is red shifted. Okay, so remember, when we red shift something, it's moving towards the longer wavelengths, or we can say to the to the lower frequency, right? Now they say to us, is the star moving away or towards the Earth? So that will definitely be away from the Earth. That's what redshifting is telling us. Now they say use the Doppler effect to explain your answer. Okay, so remember, all we're simply going to state in this case is that redshift. Okay, so when we redshift, we move away from So this is a move towards the longer frequency, the lower frequencies. The lower frequencies. Okay. Or you can talk about the frequency of gases in that case. So if we move towards the lower frequencies, that means in this case, according to the Doppler effect, okay, so according to the Doppler effect, we know that moving towards Doppler effect, rather, moving towards lower frequencies can only take place if the object is moving away. Okay, right, I'm not going to finish that up. You can actually complete that statement there. All right, and that is how the cookie crumbles in this question. All right, and let's look at the next question. All right, looking at question 7. All right, they say we've got 2-point charges, A and B, which each with a charge of 3 times 10 minus 9 coulombs, are stationary on a horizontal surface. They say to us point P is r meters from charge A and 2r meters from charge B, as shown in the diagram. Right, now the first thing they want us to do is to describe an electric field. We know that this is the area where electrostatic force is felt per unit charge. Right, so they say draw the resultant electric field pattern due to charges A and B. Now remember, both of them are positive, so that means that, all right, so let's do this. Okay, so I'm going to say that's A and that is B. All right, so we know because of them, both of them being positive, what we're going to do there is just show the result. Okay, so because they are positive, remember that the field lines would actually not would be moving outside of the field, right, of the sphere rather. And please, you remember that field lines may not cross each other. Okay, so that's what that looks like. Okay, all right, so that is what it would look like. Okay, so I'm just trying to draw a proper one there. All right, so yeah, you can actually, if you want to, just add in some more lines there. The fact is, because it's a positive charge, you just need to indicate. So the density of the of the field lines must be equal in this case, so that it shows that the two charges are actually equal, right? Okay, and the field lines are moving out because are moving away because it is positive, right? So let's go on to the next one. They say calculate the value of R. Oh, actually they told us first that the magnitude of the net electric field at point P is 27 newtons per coulomb, right? So now I want you to please keep in mind. So if we're looking at point P, remember, what do we always assume? We always assume that we've got a positive test charge. So we've got A on this side being positive. We've got B on the other side also being positive, right? So what would so we actually have to imagine a positive test charge there, an imaginary charge, isn't it? Okay, so imagine that this guy is positively charged. What would happen to the point charge P because of A? So A would actually push this guy away. All right, so I know that A would push this guy away, so the field due to A is in that direction. But what would B do, right? So if you look at B, also positively charged, so what would B do? It would actually push this the other way, and the distance between P and B is much bigger, so meaning the field would actually be smaller. So now the field due to B, right, would be in that direction. Okay, this thing is refusing to make a straight line for us. Okay, so the field due to B would be actually smaller, right, in this case. So what would be the net field B? So the net field would actually be this one over here, right, in the direction of, well, towards the right. So this would be our E net. Okay, right, because it would be the field due to A minus the field due to B, right? Of course, considering that we take that direction as a positive, right? So field due to A, that's KQA over R squared, right? So this is going to be 9 exponent 9, 3 times 10 negative 9, divided by, now remember the distance there was going to be R, okay, away from A, so that's going to be R squared, and the field due to B, that's again 9 times 10 exponent 9, exactly the same thing, right? The only difference now is that the distance there is 2R, okay, so it is 2R away from P, okay, so that would be right. So if you take this and that, they would actually cancel out, give us 1, all right, and in this case we've got 9 times 3, which is going to be 27 over R squared, and here again, what do we have? We've got 27 over 4R squared. So remember, what did we have as E net? E net was EA minus EB. So that's 27 over R squared minus 27 over 4 R squared. Okay, so this would give us the difference between them would be the field that is given, which is actually 27 newtons per coulomb. Right, now of course you do this any way that you like, right? If I look at that, I see all of them are 27. You can divide by 27 all throughout, so that will give me 1 over R squared minus 1 over 4 R squared, which will give me 1 actually. Okay, so let's try and work around this. So you've got 1 over R squared. Okay, in fact, what you can do is that you can multiply everything by R squared, right? So if I multiply by R squared, what I do on the left, I do on the right. Okay, so I end up with, okay, so the R squared would cancel with this one, would cancel with that one. You end up with 1 minus 1 over 4, which gives you 3 over 4. So the R squared would cancel that, would cancel that. So we'd have 3 over 4, which is equal to R squared. And of course, we can take the square root on either side. Okay, so that's going to be root 3 over 2. Okay, so which means that's going to be, I think this is 0.7. Okay, square root of 3 over 2. no, actually that was supposed to be over 4. Okay, so that's 0.866. Okay, let's say 0.87 meters. Okay, right, I hope that was correct. Of course, you can work this out in whatever way that you like mathematically. Okay, this is how I chose to solve it, and you get to the answer. All right, now let's go to the next question. They say calculate the magnitude of the net electrostatic force that an electron would experience if placed at P. Now remember, in this case we know that E is equal to F over Q, right? So this is F over Q. Right, so now we've got the net electrostatic field at that point, which was 27, right? We want the force, but they say calculate the force when we place an electron. What would be the charge of an electron? That would be 1.6 times 10 minus 19. Remember, you're given this value here. That's the charge of an electron, and of course we can cross multiply the two. So we've got 27 times 1.6 exponent negative 9. Okay, let's see, let's try and put this. All right, so we've got that's 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so all right, so that would be 4.32 times 10 minus 8. That's newtons. Right, so we did they say magnitude of the force? Right, so yes, they just said magnitude, so it didn't really matter what the direction is. All right, so I'm just going to leave it at that. Okay, so that is the magnitude of my force. All right, but otherwise, whatever the field, the net field was, if we put an electron there, it would go in the opposite direction of that electrostatic field. Obviously, because we assume a positive test charge, but in the case of an electron, it would be negative, right? So that is question 7. I hope that you guys really enjoyed it. Question 8, let's go. So they say the circuit below shows the battery with an EMF of 12 volts and an internal resistance of 0.5 ohms connected to 3 resistors, a light bulb, a switch, an ammeter, and connecting wires. They say the ammeter and connecting wires have negligible resistance. Right, now they say state Ohm's law in words. So remember, we say that the current across a conductor is directly proportional to the potential difference provided that temperature remains constant, right? So they tell us that switch S is initially closed, right? So they want us to calculate the total external resistance in the circuit. Now, firstly, right, someone was asking me the other day about conventional current. We always assume conventional current, okay, unless otherwise stated. But really doesn't really matter whether you chose to say electrons, move from the negative, or whether you say using conventional current, we're starting from the positive. It really does not matter at the end of the day. Right, now what I want you to notice, ladies and gents, is that, okay, so suppose that we say current is moving. Okay, we know total current would be moving from our external circuit. Okay, so now we get to this node, what happens? Right, we know definitely we're going to divide the current. Okay, so some of the current comes through here, all right, while some of the current would go through that node over there, right? Okay, so notice now the yellow current further divides, okay, and then we've got, okay, let's use a different color. All right, yeah, let me just use the black there. Okay, so there we go, right? So the yellow and the black current, the green and the black current, in this case form the yellow again, because that current, those two currents divided, and they are now once again meeting at that node there. And again we've got the blue current and the yellow current meeting, and they had split at that point. They're forming the red current again, and that's what goes back into the battery. Okay, right, so now what happens? So I know that R1 is in parallel to R2, right? But once we combine those two resistors, they actually form a resistor that is in series with the RL, okay, that 10 ohm resistor there, right? So I want us to be aware of that. So I know that I'm going to have, all right, let me just do this. Okay, so once I combine those resistors, the parallel combination from R1 and R2, and I include RL, those would be in parallel to R3, right? So we need to be always mindful who is in parallel with whom, right? So let's start with the first one. So I'm going to say for 8.2.1, okay, RP, that's going to be R1 times R2 divided by R1 plus R2. Okay, so that's going to be 10 multiplied by 10 divided by 10 plus 10. Okay, that would give us 5 ohms, right? But we know that 5 ohm resistor is in series with RL, okay? So which means these two made, okay, these two made one resistor, which is 5 ohms, and now it is in series with that RL. Okay, so I'm going to say, right, a series would be RP plus RL, and so that would give me 5 plus the 10, which would give me 15 ohms. But now that 15 ohm resistor is now in parallel with R3, which is also 15 ohms. So we're going to say, right, so which means R external, right, would now be a parallel of two combinations, which is that RS times R3 divided by RS plus R3. Right, so that's going to be 15 times 15 divided by 15 plus 15. Right, it's really worthwhile, guys, to look at this circuit stuff. It really would save you a lot of heartache. So we realize that our external resistance should be 7.5 ohms. Right, now please keep in mind, sometimes the examiners become a little bit pedantic, right? So you can use 1 over RP is 1 over R1 plus 1 over R2. Okay, at least use that once so that we know that this is the formula to use, right? Okay, so we've got the external resistance of the circuit. They say calculate the reading on the ammeter, right? Now, remember that we're looking for the total current, right? And we're given the EMF, so we can say, right, for 8.2.2, okay, I'm just going to move this a bit. Right, so for 8.2.2, we've got E is I into R plus internal resistance, right? So EMF is 12. That's 12. We want the current. External resistance is 7.5. And our internal resistance is 0.5. Okay, so to get the current there, 7.5 plus 0.5, that would be 8. So this would be I times 8 is equal to 12. And of course, we'll divide both sides by 8. And so I, that is actually, right, that's 3 over 2, which is 1.5 amperes. So the total current that we have there is 1.5. Okay, right. So the next question, they say the power dissipated by resistor R3. All right, so now we have to find out what is, the voltage. Okay, we can either find the external voltage in this case, or, and by the way, if we found the external voltage, it would be the same voltage across R3, or if you wanted to, you can find the current that is moving across R3, and you can use that current there, right? So because we're looking for power, okay, so that's 8.2.3, right? Let me look for V external. We know that it's going to be I total times R external, right? This is what we just found there, which has the total current. So I'm going to say this is 1.5 multiplied by the external resistance. Remember, this was 7.5, right? Okay, so I'm going to say that's 1.5 times 7.5, and that gives me 11.25 volts. Now, because those resistors were in parallel, it means the voltage would be the same, right? And which voltage would be across R3? It would be that V external, right? So I can say, right, in this case, I can say, well, to find power, it would be V multiplied by, not the current, rather, it would be V squared over R. And so that would be 11.25 squared divided by the resistance. Now remember, our resistance is 15 there. But what you could, as I said, what you could have done was to find the current that passes through that resistor. And please try to do that and tell me if you do get to the same answer. Okay, so that's 11.25 squared divided by 15. Okay, I get power of 8.4, let's say 8.44 watts. Okay, please remember power is measured in watts. And guys, you don't want to drop, just unnecessary marks on, SI units. So please make it a point that you get those correct. All right, let's go to the last point. They say switch S is now opened. Okay, so the moment we open switch S, what happens? There's no current that is flowing. Okay, so this resistor is as good as non-existent, right? So we've got that total number of resistors, right? Which is R1, R2, as well as RL. So once you remove a resistor that is in parallel, remember what happens to the external resistance? It would increase, right? Because now you'd have 15 as your external resistance, because you'll have this 10 here, okay, plus the combination of these, which is 5, okay? So it means that our R external has actually increased. Right, now they wanted to know, they say if the resistance of the light bulb remains constant, how will the brightness of the light bulb be affected? Remember, the light bulb is RL, okay? So they want to know how will the resistance of the light bulb be affected. So now want to see what happens to the current that was passing through there. Right, so when we increase the resistance, all right, what happens to the total current? The total current decreases, all right, but you do remember that the current that was passing through there, the current that was passing through the resistor had to split between these 2 points, right? So there was current passing through here, and there was another current passing through there. Okay, right. Now, what would happen in that case? Definitely, there's no longer current that is passing through here. So the total current would actually pass through that resistor there. Okay, and in that case, which means that we would definitely have an increase in the power, okay, which results in it burning brighter. I really don't like this question again. All right, for examiners, they really need to be mindful again when they make these type of questions, because you don't want a question that would require one to really calculate, because this wouldn't necessarily be really straightforward. Okay, so they said if the will it increase, decrease, or remain the same? It would definitely increase. Okay, even though the current has decreased, right? Even though rather the resistance of the circuit has increased, right? We actually know that it's still the total current that would pass through that resistor there, okay? The current would decrease, but it's the total current passing through there. So again, I'm really not too happy about this question. All right, so they say explain your answer. All right, so we know that I is equal to V over R, right? So what happened in this case? We know that removing that resistor there will increase the effective resistance of the circuit, okay? Even though the total current decreases, but we've got the total current that is passing through that resistor, and we know that V is equal to I times R. R remains the same. Current has increased passing through there, and so the voltage would also, power would increase. P is equal to V squared over R, okay? Or in fact, let me say I squared R, okay? So an increase in the amount of current. Now, please remember, I was talking about the total current here, right? But remember, the total current now passes through this guy here, and so the power would actually increase, okay? So it would burn much brighter. All right, so that is how the cookie crumbles. Guys, and I really do want to implore, when examiners ask specific questions, they always need to be mindful of, the explanations there. It's not really easy to answer that question without necessarily a calculation, but look, it is what it is. Okay, that's one of the contentious issues that would always come across. All right, I hope that made sense. Let's move on to question 9. And now we'll look at question 9. So we've got a simplified diagram of a DC electric motor that is shown below. Right, it's been a while since they've asked us about DC motors. Okay, so they say to us, write down the name of component A. And remember that component A, that is a split ring. commutators there. All right, so you can write the split rings, or you can say commutators. Right, so they say state the energy conversion that takes place in this motor. Okay, we know that that would be from electrical energy to mechanical energy. They say in which direction will the coil rotate? Choose clockwise or anti-clockwise. So remember, first of all, we know that our current value, right, would move from that direction. Okay, so we know that, say for instance, in that, on that side, let's call it side AB, our current is moving, we can say inside the page, right? So if you take your second finger on your left hand and point it towards the page, inside the page, all right? And then secondly, we know that, our field, magnetic field, always moves from north to south. Now this is represented by your index finger, right? The one next to the thumb, so that would be pointed that way. Okay, and your second finger is pointed in that direction. You'll see that your thumb kind of points upwards, right? So if that's the whole of your hand, your thumb would be pointed upwards. It's showing you that this side would actually go up, so therefore it means that this is rotating rather clockwise. Okay, so our answer there should be clockwise. They say state two changes that can be made to the motor for the coil to rotate faster. Well, certainly we can use a battery that has a larger EMF, or secondly, what we can do is we can increase the number of turns on the coil, okay, or not number of turns, rather, number of coils that we make, right? Or we can use a stronger magnet, right? So that is how we would improve that. All right, let's move to the next portion. They say the circuit diagram shows an electric kettle and a toaster that is connected to an AC source with RMS voltage of 220, an emitter connecting wires switches S1 and S2. Okay, right, so now they ask us define the term root mean square current, right? So remember, these definitions are really not the most popular. We say that the root mean square is the DC current that dissipates the same amount of power as the average power dissipated by the alternating current. Okay, right. Of course, other books use different definitions, right? You can use the one that you're comfortable with the most. Right, so 9.2.2, they say when the switch S1 is closed and switch S2 is open. So we close S1, right? And they say S2 is open, right? They say the maximum current through the circuit is 3.6 amperes. Now they want us to calculate the root mean square current in the circuit, right? So remember, they've given us the maximum. So we know I RMS would be I max divided by square root 2. And so our maximum is 3.6. We divide that by root 2. And let's find that value. Okay, I get 2.5. Okay, let's say 2.55 amperes, right? Okay, so they say to us, when switch S1 is open, right, and switch S2 is closed, the root mean square current is 2.62, okay? And they want us to calculate the energy consumed by the toaster. All right, so to get the energy, in this case 9.2.3, all right, so we know the voltage, and we know in this case the current that is dissipated, right? Okay, so what we would need to do is we would say, right, to calculate the amount of energy that is consumed in 2 minutes, we can say, well, that's going to be VRMS IRMS multiplied by time. Okay, so that's VIT. Okay, and in this case, what we can simply do is take our current. We're given that to be, well, the voltage is 220. The current is 2.62. And the time is 2 minutes. But remember, that should be in seconds. So we multiply that by 60, right? So that would be 220 multiplied by 2.62 times 120. Okay, and we get an amount of energy, 69,168. And remember, this is energy, so it should be measured in joules. Okay, right, and essentially that is how the cookie crumbles when it comes to this question. Right, let's go on to the very last question. All right, and we finally look at question 10. Right, so they give us two small spheres, which are A and B, that are made of pure zinc, that are at rest 0.1 meters apart on a wooden table. They say sphere A is negatively charged and is free to move on the table, while sphere B is uncharged and fixed on the table, right, as shown in the diagram. Right, so they say high intensity ultraviolet light of frequency 2.8 times 10 to the exponent 16 hertz is shown continuously on to sphere B, and they say the work function is 6.63 times 10 minus 19 joules, right? So they say to us, define the term work function of a metal. So remember, by definition, the work function is the minimum energy that is required to emit electrons from a metal surface, right? All right, so I will not write that one down. I know you guys probably know it. Okay, let's go on to 10.1.2. They say explain using a suitable calculation why ultraviolet light shone onto sphere B will eject electrons from its surface, right? So first of all, we were given the work function, and they said to us the work function is 6.63, okay, times 10 minus 19 joules, right? And so all we need to do is to calculate the energy of the photon, right? So we need to now find out what is, in fact, let's do this, 10.1.2, right? So we need to find out the energy of the photon, and we simply do that by calculating E is equals to HF. We know H is Planck's constant, 6.63 times 10 minus 34. This is a constant that's given to us. This is multiplied by 2.8, all right, times 10 to the exponent 16, okay? Right, so in this case, I want you to note, if we can find out that the energy of the photon is greater than the work function, then definitely electrons will be ejected, right? So let's do that on our calculator, right? So we're going to say 6.63 exponent minus 34 multiplied by 2.8 exponent 16. Okay, we get that value. Okay, let's find out in detail. That value gives us 1.86. There it is in scientific notation right at the bottom there. 1.86 times 10 to the exponent 17, right? So in this case, that's our answer. Okay, so this is 1.86, if I'm correct. Yes, 1.86, yes, times 10. So we should give our answer correct to 2 decimal places as per the instruction of the invigilator. Right, now please, I want you to note the fact that it's exponent minus 17, right? It simply shows that it is much, much bigger than this work function here. So we know definitely that E is greater than the work function, and so therefore it means electrons will be ejected, right? Of course, what you could also have done, electrons will be ejected, will be emitted rather, okay, emitted. Okay, I hope that I'm spelling that the right way. Right, anyway, going on to the next question. So another way in which you could have done this is you could have proven that the frequency of the of the photon, right, the frequency of ultraviolet light is greater than the threshold frequency. So you could have also calculated the threshold frequency by simply saying HF0. You've got the work function, you've got Planck's constant, and you can find out what that threshold frequency is, and you'll see that the frequency of the electron, the frequency of ultraviolet light is greater than the threshold frequency, and you can make the same conclusion, right? All right, now going right along. Okay, so now we go on to question 10.1.3. Right, so they ask us the following question. They say sphere A carries a charge of 5.4, negative 5.4 rather, times 10 minus 6 coulombs, and requires a minimum charge, or rather a minimum force of 0.027 times 10, 0.027 rather newtons to move from rest, right? They say to us, calculate the minimum number of photons of ultraviolet light that must strike sphere B, which will cause sphere A to move from its rest position. Now, ladies and gents, I want you to note, I think the trick of this question lies in the word minimum, right? And here's the assumption that we're going to make. That one electron, or rather, let's say one photon, will eject one electron. That's the minimum that can happen, right? But usually that is not the case. You'd find that one photon does manage to eject more than one electron, right? But of course, because they have said to us minimum, right, I am going to assume a 1:1 reaction, or a 1:1 ratio between the two. Right, so the question is, how many electrons can we actually eject here? So if I can find out the number of electrons that can be ejected, then I can then assume that that will be the same number of photons that will be ejected, right? So we've got the force, we're given the charge, right? So let's do this. We know from electrostatics that F is equal to K, Coulomb's law, Q of A, Q of B, divided by R squared, right? So this is 0.027. That's 9 exponent 9, right? Now remember, the charge of A, which one was given? Yes, the charge of A is 5.4 times 10 minus 6. So that's 5.4 times 10 minus 6 multiplied by the charge of B, right? So remember, we are looking for the electrons that will be ejected in B, right? So divided by the distance between them, we're given as 0.1, and so that is the distance. And please remember to square it, right? So we're going to do some gymnastics there mathematically, right? So we're going to say, right, so cross multiply those two, 0.027, okay, multiplied by 0.1 squared, okay, right. And please remember, once I've calculated that value, this is what's on my right hand side, and in this case I've got that 9 times 10 exponent 9 multiplied by 5.4 times 10 minus 6, right, multiplied by the charge of B, right? So it means I need to divide by this entire expression, right? 5.4 times 10 minus 6, okay? But remember what you do on the left, on the right in this case, you do on the left. So I'm going to do that on the calculator, okay? And please you're more than welcome to join me in this. Right, so we found the answer and we divide that by, okay, I'm going to put that in brackets, 9 exponent 9, okay, multiplied by 5.4 exponent minus 6, okay, and I get, okay, let's put a better detail to that calculation. So this is 5.56, so the charge of B is 5.56 minus 10, right? So I'm looking at that scientific notation there so that our answer is not confusing, right? So this is the charge in terms of in coulombs for this for the number of electrons that have been ejected. But remember, how do we get electrons that are ejected? So to calculate the number of electrons, right, from electrostatics, we know that the charge of B divided by the unit charge of an electron. So that means that the charge of B, 5.56, okay, times 10 minus 10, divided by the unit charge of an electron, which is 1.6 times 10 minus 19. Now you might say to me, yeah, but why is it not negative? Well, it doesn't really matter in this case, right? We are just looking for the quantity of the charge, right? And I have divided by the unit charge of an electron, right? Just the magnitude of it, okay? So that I get a positive number of electrons, right? So from our previous answer that we got, right, I'm going to divide 1.6 exponent minus 19. Okay, right, that's a huge number. Okay, let's do this just to get a better detail of it, and I'm going to look at it in scientific notation. So the number of electrons that have been ejected is 3.47, right, times 10 exponent 9 electrons, right? So remember our assumption that for every one electron there is one photon, because we're looking for the minimum. So which means the number of photons, the minimum number of photons, okay, will be the same as the number of electrons. So that's 3.47 times 10 exponent 9. Right, so photons. All right. I hope that makes sense, guys. Right, so moving right along. Okay, right. So now we come to 10.2, and we say a beam of white light is shone onto a cold gas. Okay, please note this. Cold gas. Right, so the emerging light is dispensed and a line spectrum is observed. Right, so remember, what are we doing in this case? When we pass this light through a cold gas, some of the frequencies are absorbed, right? So they say to us, name the type of line spectrum observed. So this will definitely be a line absorption spectrum. Okay, remember that in line emission, in this case, what we do is we take a gas, right, and we pass it through a current. So we give it electric current, and in this case it will emit the frequency that the gas has, right? So they say name, or sometimes they may talk about a hot gas, right? So in this case they spoke about a cold gas, right? So they said name the type of line spectrum. So this would be a line absorption spectrum. They said describe the spectrum referred to in question 10.2.1, right? So in this case, what happens is that when electrons, okay, or rather when the frequencies of light in this case are absorbed by the gas, right? The gas will also show us in this case lines, okay? So we'll observe a rainbow. If you want to put it in inverted commas, you'll see a rainbow with one of the colors that are missing, right? So the one that has been observed. Okay, right. So that in 10.2.3, now they say to us the diagram below indicates some possible energy transitions made by atoms, right? So they say which one of the diagrams could result in the type of spectrum observed in question 10.2.1, right? Choose diagram A or diagram B. Right, now if you look at the two, in diagram A you've got energy, right, transition from higher energy to what we call the steady state, or in this case to the lowest energy transition. And what it does is that energy will be released in this case, so it will emit energy. So this is definitely line emission spectrum, right? But in this case, when you look at the transition that is happening in B, this is when we are going from the lowest energy level to higher energy level, and in so doing we require energy, so energy will be absorbed. So definitely diagram B is the one that has to do with the transition that we spoke of. Okay, right, I hope that makes sense, ladies and gents. It was a very interesting paper out of 150. All right, so I'll come back again with chemistry, right? Please tell all your buddies that Uncle is back, okay? And I'll be giving you more content when it comes to science and mathematics, and I'll make sure that I answer all your questions in relation to this. And by the way, for those of you that are upgrading, please make it a point that you try and work as hard as possible, but I will ensure that I bring you all the things that you need in terms of the upgrading information, and just to advise ourselves now and then as to what we need to focus on. Otherwise, from me for now, I'll see you guys next time. Sharp, sharp.